Why visit Mount Moffatt? So my father wrote a number of books set in this area. Dad set some books in this area. Arnold, my older brother, wanted to go and visit some of the places that were mentioned in the books. And the previous time that he and I had been to this area, I was about this high. So about 4 or 5 years old. So it'd been a while. The Mount Moffatt section is the parks map. Is a bit limited in terms of the hikes that you can do. The longest one is to the tombs, and that's probably an hour and a half, depending on how long you spend at the tombs and the Looking Glass. And the others are shorter. And being the adventurous types, we started looking for something else to walk to. And we started looking at Google Maps.
Making the site to go up back in canoe shape.
And my older brother, with quite a scientific mind, went looking for information on impact craters, because when you looked at the aerial photos, you could see these round shapes everywhere. No information whatsoever about impact craters in any of the national parks brochures, which in many respects is not surprising, because unless something has actually been proven, they're not going to mention it. There is one paper by Professor Glickson that lists what he believed at the time to be all the known craters and possible and probable craters in Australia. And in that paper, he listed a Mount Moffatt crater as probable. And it gave coordinates, and we matched that to one of the shapes in the photography. But as far as I know, Professor Glickson has never been to Mount Moffatt. He put it in the list because someone told him to. Now, Alan Glickson is fairly well known in these circles, but his speciality is human development, not impact craters. But he's well known in impact crater circles, so much so that someone actually named one after him in Western Australia. So, we think he knows what he's talking about. Okay, so identifying impact craters. There are certain things you need to look for to be able to say this is an impact crater. So you need to think about the types of what are called ring structures. All right, so before you can say it's a crater, you call it a ring structure. All right, so there's 3 main things that cause ring structures to appear in the landscape. All right, volcanoes, impacts, and escarpment retreat. But that last one is like 90-something% of all the ring structures. All right. So volcanoes, 3 dominant types. All right. Shield volcano, so the Buckland volcano, which is just on the northern edge of the Mount Moffatt So the centre of it is just to the north of the Mount Moffatt Park, section of the park, is a shield volcano. So shield volcanoes, generally it's a hole appears in the ground for whatever reason. It could be that the plates are stretching, right? And the lava comes up and it floods the landscape. Right, that's a typical shield volcano. Main range, focal peak, Mount Warning, shield volcanoes.
Why?
Yeah, yeah. You get the classic cones. So Mount Taranaki, also known as Mount Egmont, Mount Fuji, all right? Big cone, right? Big peak in the middle, right? Whereas a shield volcano is much more rounded, right? And then you get the calderas. So Lake Taupo, Rotorua, Yellowstone.
The drainage pipe, the vessels steady at high speed, the side of the top of the boiler would swallow the concertina.
Okay, we've got someone who hasn't muted. Can you please mute, please? So what you've got there is a magma chamber under the ground, a thin bit of crust on top. The magma chamber pressurizes up, cracks the ground at the top, and then for whatever reason, the magma chamber empties and the roof collapses. And that's caldera.
Just as an aside, what are the lava tubes in North Queensland? Which type? Don't worry about it.
Well, that's a lava flow. So that could be a shield or it could be from a cone. Right. And then impacts. So there can be human caused impacts. So things like artillery shells, right? Nuclear bombs. Or if you want to go to the absolute extreme, Messines Ridge. Anyone know about Messines Ridge, World War I? The Canadians and the New Zealanders dug underneath the German trenches and set a massive bomb underneath. When they let it off, it was clearly heard in London. The largest explosion caused by humans other than a nuclear bomb. All right. And then there's the extraterrestrial impacts. So meteorites, comets, where something comes through the atmosphere and goes splat. Sorry, all your dinosaurs are extinct. And then there's escarpment retreat. So erosion, just taking bites out of the hill. All right. But then you've also got an older strata, and then a new strata comes over the top. Now that happened here right now. Would that interface between the older strata and the newer strata be perfectly flat? Right? No, it won't. All right? Think of Mount Gravatt. All right? You surround that with a fresh layer of sandstone. All right? And the sandstone, let's say it hardens really hard, but Mount Gravatt itself is a bit softer. It erodes out, it's a weak spot. And oh, look, nice round hole in the remaining sandstone. All right, looks like a crater, but it wasn't a crater. All right. So every time you look at one of these, you got to have in mind, how did this form, to work out what type it is. So the things that you start looking for. So if you find one of these things, you know you definitely have an impact crater caused by a meteorite. So shadow cones are the only one of these that you can see without a microscope. And that is a lovely example of a shadow cone. I have no idea where that's from. It's just an image I found on a search. Shocked quartz. So if quartz gets hit by a high pressure impact, the crystalline structure will change, and that is distinctive under a microscope. And so that's one of the things that you look for, but you have to drill and you have to have the microscopes. Pieces of the impactor, right? Its chemical makeup is different. It's usually fairly obvious. And then iridium. So iridium is an element that is relatively rare on Earth, but significantly more common in the solar system. So the Chicxulub crater is a classic example of finding things by seeing the iridium. So the layer in the geology that marks the end of the Cretaceous, beginning of the Paleogene era, there's this layer with a huge spike, 100-fold spike in the occurrence of iridium. Right. And finding that, they then went looking for where is the crater. And I won't go into too much about that because that's Keith's talk. Okay, so what else can you look for? Right, that might get you into the probable category. So if you've got a layer of rock strata with a nice, fairly consistent dip, angle, and direction, which is what we have at Mount Moffatt, then unusual, sudden changes in dip, angle, and direction, particularly ones that make a nice circle, are things that you'll look for. Right. Heat effects, melting. So you're looking at the original strata, you're looking at this strata and seeing differences in that strata. And also shows a photo later of one of those. Ejecta, so pieces that have been thrown out. And then topographic anomalies, something that the pattern of the landscape is disrupted. What's disrupted it? There needs to be a reason. Okay. A little bit of orienteering. Geology affects landform. All right, the image on the left is classic sandstone terrain. That happens to be an area near Rathdowney. And you can see in that the layers of the rock features, there's three different, if you're really observant, there's three different outcropping layers, two more easily seen. The third one's a bit lower down. You'll also see a well-developed drainage pattern. All right. The middle image. This is at Old Hiddenvale on the Little Liverpool Range. The top of the range is a basalt flow lying over Marburg Formation sandstones. The rock down there, that's sandstone. So you've got sandstones in here, you've got basalt flow up here. All right. You can see the difference in the landform shapes of that basalt flow. Yes, it's been cut by a few valleys coming up from the sandstone, but it's all that bulbous shapes, flow shapes are distinctly different to that sandstone terrain. And then on the right, up near Stanthorpe, is a classic piece of coarse-grained rose granite terrain. And here what you see is every change in slope is associated with an outcropping of rock. You see a drainage pattern that is immature, and the predominant drainage pattern is associated with fracturing in the rocks. All right. So those patterns are very different. All right. And after 50 years of orienteering, I can tell, like, I walked across, it was a bit up here somewhere, but like I walked across this boundary and I stopped after like 10 meters and went, there is the geology, at least in the soil, boundary. And I was going to myself, why? Why? The trees are the same, but the grass on this side was taller, healthier. I was getting spear grass in my shoulder. On that side, it was down here, it was struggling, and there were termite mounds. On that side, no termite mounds. This side, termite mounds, regular. So, like that, I could tell I walked across a geological boundary. All right, let's look at the geology of Mount Moffatt. So it's dominated by sandstones. Mostly Serac Basin sandstones. And we get three layers in that. Prepivus sandstone, right? So Carnarvon Gorge, right? At Mount Moffatt, it's not quite as tall, but it's still that same classic cliffy type terrain. Above that, you get the Evergreen Formation, which includes Boxvale member. Doesn't outcrop as much. And then there's another layer above that, the Hutton Sandstone, which is only in the eastern part of the park. Below that is the Bowen Basin, the older ones. And the Malayamba Formation, I hope I've pronounced that correctly, limited area. The most prominent outcropping of this particular formation is a feature called the Mansions. and it's very erodible. In fact, from bottom to the top, so the precipice is the least erodible of those on screen. And then on top of that, you've got the basalts from the Buckland Shield volcano. And courtesy of Warwick Wilmot and his very excellent book, we have this diagram here. And I strongly recommend this book and the one for Southeast Queensland. If you don't have one, you should get one. If you want to know about geology in Queensland, it explains a lot quite well. So yes, this is Warwick's diagram of the Central Queensland Sandstone Belt and the different layers in the sandstone. So it's only down to the Malayamba that we get in Mount Moffatt. And then Warwick has used similar colours to the official geology mapping. So Mount Moffatt section of Carnarvon National Park is this piece. And we can see the big area of green, that is the precipice sandstones, the blues, the evergreen, and the boxvale. The orange is your basalt. And the Buckland Shield volcano is just off, the center of it is just off to the north from here. All right, so general idea of what the geology is doing in the area. So what does the landscape typically look like at Mount Moffatt? So this is an image from Queensland Globe showing some of that precipice sandstone area and the typical pattern that we see in those precipice sandstone areas. So you've got large sandstone cliffs. So they're 30 to 40 metre, whereas at Carnarvon, they're bigger than that. Complex ridge lines. Those ridge lines all join up. Broad flat valleys. So you think about when this was being deposited, where the precipice sandstone ridges are now, these were valleys. All right, so if you invert that landscape, here are your drainage lines, now ridges, and here were your ridges, now valleys. And this photo is taken not far from Marlong Arch. So you've got an isolated piece here on the left of the sandstone cliffs. The main cliffs you can see in the background. One of the things to note here, we noticed this when we're out there, no boulders. All right, piece breaks off, falls down, and it erodes out really quickly. All right. Everywhere you go, particularly at Mount Moffatt, finding a boulder is very rare. Okay, let's look at the boxvale. So low height cliffs, right, 1 to 2 meters. Complex valleys. broad, flat ridge tops. All right, and here's a photo. As we were walking into one of the craters, we were looking at what the topography was like outside the crater that we were going to. So this, the photo taken for that reason. You can see how low these ridges are. You can almost look up onto the top from the bottom. They're lower than the trees. I haven't, unfortunately, at this stage, got a photo of the basalt terrain because I haven't got up into there just yet, but aerial imagery, contours, all right, so stepped lava flows. All right, so the center of the volcano is up there. You've got lava flows coming out and then lower down as well. So, you know, the lavas come out in waves. But there's, you know, it's flows, all right? The lava goes downhill, all right? It floods the valleys, all right? So it'll, again, invert the landscape. And one of the things I noticed is that most of the basalt at Mount Moffatt is at 900 meters or above, and that almost everything above 900 meters is basalt, and almost everything below 900 meters is not basalt. And the Buckland Shield volcano erupted 27 million years ago. So there's been a little bit of erosion. So, you know, you get sort of cut-offs like here, where the erosion has taken out a narrow bit in the ridge. Okay, let's start looking at some craters. So we'll start with the one that Professor Glickson put in his paper. And we'll start by looking at the 1 to 100 thou geological mapping. So we've got Boxvale, sandstone. This is showing a bit of evergreen as well. Can't say that I really saw that in the landscape, but anyway. Some precipice, particularly up this side. And you see that there's this hole. All right, and they've mapped colluvium in here. Well, where's the colluvium come from? It's come from the crater walls eroding down in. And they've shown some fault lines. Basically, they've agreed that there is a circular pattern in the shape in the terrain here. So let's look at that without anything drawn over the top. We're just looking at the imagery. Right, we looked at that and we went, well, yeah, we can see stuff here, but not convinced that that's the actual edge of the crater. So we've got a large hole in the ridge. We've got some compression, distortion around, particularly that side. Significant erosion of the upper layers. Inside is flat. Okay, it's got a bit of a slope out to the northwest where it drains, but if you go north-south, it's flat. The underlying prepivus sandstone is less eroded. And we walked half the rim. We can see in the photography 3/4 of what we believe to be the original rim of the crater. And the colluvium in the middle. It's all filled in so that you can't see any sign of big areas of melting. Let's look a bit closer. All right, so here's that distortion area in a bit more detail. This is what I mean about it being flat. And then you come to this. All right, it's a boulder and a couple of cliffs. There's a couple of lines of these rocks. It's like, what? What's this doing here? All right. And you look at that rock closely, you go right up to it, and all the fracture lines, they're all sealed. They've been joined back up. So, okay, how did that happen? Quite possibly. You have to convince some geologists of that. And then we come to this. We walk in towards the center. Now, to my untrained eye, I call this the shadow face. Right, as we progressively walked in, the dip angles have increased. And then we get to this, and everything is smashed. And some of it has clearly slid down this face. I think this is the crater face. And we found these in fits and starts, which you can attribute to the ridges in the original prepivus sandstone terrain, as to why it's in fits and starts, for half the circumference. Right. So on the left, the red line is where we believe the actual crater is. You see on the right, all the arrows pointing, they're our observation sites. All right, so the photo of the boulder is number 3. All right. The photo of what the boxhole formation terrain is like is photo 1. All right, we went from here, dip angle, 1 degree. All right, we came to number 2, dip angle 1 degree, but opposite direction. We get to 3, dip angles more like this. All right, we get to 4, shadow face. And then as we go around, we find more spots. There's another shadow face there. Various rocks, shadow face all around there. More rock here. And then if you look closely in the photos, you can see it extending around there and potentially around here as well. Now, this crater is listed as probable already. There was clearly not going to be any shadow cones. So we got to the point of going, well, the only way you get any more information on this is by drilling. And that requires quite a bit of money and a special permit. And we don't have either. So this is as much as we can do on this crater. All right. But it gave us a couple of things. It gave us that the different layers in the sandstone are eroding at much dramatically different rates. So the box fail has eroded back 600 to 800 meters, whereas the Prepperfest sandstone, it's eroded back 100 meters, if that, in this case. Which then became useful elsewhere, looking at the fact that, hey, it's not one uniform erosion rate. And in some instances with the basalt, you're talking tens of meters at most. Any questions about this crater?
100 million years ago?
Okay, so after going here, the next day we went to Carnarvon Gorge and we happened to run into Dr. Will de Vries from University of Queensland, who is now assisting us with this project. And he said to us, a crater more than 10,000 years old, you won't find evidence on the surface. So, based on that advice, this is somewhere around that 10,000-year-old, maybe a little bit older, because some of these are quite eroded out, but others aren't. So without a date, I can't tell you. And to get a date, I need a sample. And to get a sample, I need a permit. And someone willing to do the testing. The red line, that's a couple of kilometres across. So Gleason lists it because he went right out to the Boxville Formation at 3 kilometres, but we actually think it's only 2.
Do you have any sense of the size of the meteorite?
Only by going to the document, what's it called? Signs of Catastrophe, I think it's called. And it has a table in it that says, based on this size of crater, therefore the impactor is this size, around the 40 to 50 metre mark, I believe. It's a while since I looked up that table, so I can't quite give you the answer exactly, but it's that sort of order. Surprisingly small for such a big hole in the ground. Yeah. Okay. Second crater. There's a lava flow with a big hole in it. Well, that's what I saw in the geology maps. How did that hole get there? So, orange basalt flow coming in from the top, and we've got a bit on the edge. So lava flows downhill. So what happens when it comes to a hole? Fills it up. It hasn't filled up this hole. Right? Everything inside is sandstone of one type or another, certainly according to that map. And I haven't got any evidence to say that there's anything basalt inside this feature, which means this feature post-dates the basalt flow. Right? So it can't be any older than 27 million years old. Right? Basalt flows follow valleys. Why does it suddenly stop? What is going on the eastern side? Right? Okay, you get erosion, right, taking out the link. But that doesn't look like what's going on here. Right? You think about the landscape formation processes here, that doesn't make sense. Not to me. The Molayamba Formation. They've mapped all that as Molayamba Formation. I strongly disagree with that. I found Molayamba Formation there, and I found it there. I found a piece here. It's a couple of pieces on this hill, and that's it. I think most of that is actually just precipice with a couple of bits of Molayamba inflated up above the surface in spots. Okay, let's have a look at that eastern side. So this looks to me like the basalt flow has spilled over the edge of the ridge. Right? Because this shape, to me, I haven't walked that particular spot, but that looks basalt. That bit, all basalt. That's basalt. Right, so it looks to me as though it's over top. It could be the end of the lava flow, and that it's just plugged the valley. But looking at Marlon Creek and the shapes in Marlon Creek, that doesn't ring true to me. There's another spot on Marlon Creek where there's a change in direction that looks far more likely to be the junction of a drainage valley. Not here. So, you know, that is anomalous. The missing ridges. Remember what I said about the precipice sandstone, about it filling the original valleys? Okay. So valley through here, right. Valley there, but they've been chopped off. They don't connect. Where? How does it get to the river? Right. I think that is where the crater ends, where the rim is, right? And these all end about the same distance from it. these ridges. And then there's these ghost ridges. The ridges continue inside, but only a short distance, and then they sort of fade out. It's like, okay, your impactor lands and it blows out, right? And the energy reduces as you go out. And something that's harder or higher at the edge isn't going to erode out as much. Right? And that's what I'm seeing. And that's one of them. There is your ghost ridge. Here we are on the rim. Right? It's not insubstantial. Right? What's the explanation for that? If it's not the ghost of a pre-existing ridge. Okay, so I picked up the rim on this one, came in from the south, turned left, picked up this feature pretty much straight away, followed it right the way around past the second ghost ridge, where you had this, and then I headed off to a different target. So I didn't complete the arc. But right through that distance, I was finding rock features in an arc, and at points, it wasn't Precipice, it was Mullumbaya. And the Mullumbaya was at the top. Right. Near the highest elevation was the Mullumbaya, and everything else was Precipice. So you can't say that this is just a escarpment retreat, because there's this bit of Mullumbaya in there. It's like, well, how did that get there? You know, if it's just a line of rock retreating, that shouldn't be there. Right? And here's the Mullumbaya. Right, clearly different. All right, this anomaly's got an anomaly within it. If this is a crater, what are these? Right? And when we were looking at that in the contour pattern, we're going, well, that can't be a crater. And then we came up on here, and we looked down into there, and we saw white Precipice sandstone cliffs in a circle, and we went, that is a crater. So what the heck is going on here? It's the same height as the surrounding Precipice sandstone cliffs. But that is not Precipice sandstone, not in the way it normally outcrops in this park, right next to it. Like here, there are cliffs. Here, there are none. When I walked up towards this hill, this is what it looked like. Right? It's nothing like Precipice sandstone terrain. Nothing like it at all. There was a rock. Notice the dip angle and direction. Right, when we found things here, the dip angle and direction were random. That is either a piece of ejecta or it's slid there. On the crater floor, there's a piece of Murrumbidgee Formation. The next nearest piece of Murrumbidgee Formation is hundreds of meters away. I suspect that is a bit of ejecta that has been thrown there. When I walked up to it and looked at it, call it the vibe, it's upside down. What we suspect, our explanation, there are multiple impacts here. This is not just one. In particular, there is a big one there. So you've got a very big one here. Something's landed there, maybe a little bit later, because otherwise, how do we get the ejector on the crater floor? And that it's knocked the crater rim over into the hole. And that this is the remains of that northern crater rim. And therefore, it should be classified as colluvium. Right? It's a giant landslide. That's our explanation for it. We probably still need to do a bit more work on it, but generally the observations on the ground are matching that explanation. Okay. We right to keep going, or do we want to take a break?
No, we've done about this thing for time, actually. Yeah.
Okay, I want to cover a couple more. I can skip some.
Do you want a break?
No, I'm fine. I'm in my element.
How many impact craters have you got here?
Well, if you count some of the multiple strikes, it's in the order of 12, 13. I've got slides for 7, which include some of those multiples.
Go for another 20 minutes.
Okay.
Why should there be so many craters in one area?
If it's a single event, which I can't see any reason why it wouldn't be, then as the object has come in, it's been gravitationally disrupted and it's broken up into multiple pieces. Probably relatively low in the atmosphere, given the spread. So it's not unusual that, Barringer is a single strike, but like there's one in Estonia that's 7. There's another one, I think, in Western Australia that's 20. So it's dependent on the composition of the object that's come in. All right, so the Japanese sent a probe out to Bashi or something, I think it's called, and they found that it's only loosely joined together, that it's polar rubble. And I think the one that the Americans hit practicing deflection, it was polar rubble as well. That they're not all pieces of a planet or pieces that are broken off in a impact event between asteroids. Some of them are just conglomerations. It's the first step in the planet formation process is that things start linking together.
Well, we saw 21 pieces of a comet that hit Jupiter,
Yes,
Shoemaker Levy 9.
correct. That was one of the other examples I've thought of. Yeah.
What is the diameter of the whole set of the fat craters? How far apart? Within 100 kilometres? Within...
Oh, no, we're tens of kilometres. Yeah. Yeah, it's like 10, 15 kilometres spread from the northernmost ones I've identified to the southern one. Yeah. Might be 20, but yeah, it's not a significant spread, which is why I said I think it's relatively low in the atmosphere where things have pulled apart. Right, and you see the videos of breaking up satellites coming in, you see it breaks up into pieces. Yeah, question up the back.
I was just going to ask, where you've got those fingers in the top
Yeah.
there, could that come about by temperature change? That when the temperature changed, it cracked because they're all interrelated. Each finger is related to the one next to it, even in the one of the
Yeah, okay. So see here you've clearly got Precipice sandstone.
movement.
Yeah, I think that's the valleys coming up here. And that your basalt is on top. Right, so we're cutting down into the sandstone underneath there. I haven't been to the spot, but that's my interpretation from the photography and the contours. Okay, so a lava flow with no sidewall. So we were just talking about the crater down bottom here, and now at the top, and there's this big escarpment, lovely curve. And you've got basalt coming in behind, and it stops. But it rises up first and then plunges. This is the geology mapping. There are some errors here. So that is Precipice Sandstone Bluff. I believe we've got some sandstone over here too on that face. And the basalt, I'm not 100% sure exactly where it cuts off, but it comes down considerable distance down that face. Now, why I talk about this is the lava flow with no sidewall. Here's a lovely diagram of a classic Precipice sandstone style valley. Right? And the lava flows downhill, follows the valleys, hills and ridges on each side. Right? And we fill this with lava. Right? We got ridge on one side, ridge on another. Okay, but, we might fill it up a bit more and it might go out to the edge or it might just tip over the edge. Right? But, I'm expecting to see something to contain that lava flow. Right? Okay. There's another image. There's more lava flow over here. This lava flow needs to get to that lava flow. Right, that's that sandstone bluff on the left. This on the right is basalt. Right. Those images are in exact correct relationship to each other. Taken from a hill on the other side. Right. Everything around to my right is basalt. What stopped that flow from not only filling this, but going on? Right. And I got evidence that it's gone on because you got basalt flows up on the next ridge way behind me. Where's the sandstone that stops that flow from going out that way? Perhaps. Or it got obliterated. What's more, on that edge, there's a volcanic plug. Just to throw more spanners in the works. Right. That is volcanic plug. Or it's an intrusion, one or the other. So this hill, colluvium. We looked at the rocks on that hill and all their random dip angles and directions, Mullumbaya Formation. My brother said to me, these rocks look like they've had a very bad day. Now, we're missing this bit, but I did a cross section. That's the cross section. If we had the other side, that's what it looks like. And if that was the case, I would say to you, that is the most famous crater on Earth, except for Chicxulub. It would be more famous than Barringer. Okay, I'm going to do this one and then we'll wrap it. And this one's important because this is the one where I'm actually going to do samples for testing. Strange bends in the river. Here's the Maranoa River coming in and heading down to the southwest. Now let's just say, for argument's sake, that we put an impact crater in here, in this gap. In fact, let's put in two. Right, bang, bang. Right, and just to be extra impact cratery, let's chuck a rebound hill in there. In the middle, Mount Sharp. So where's the river go now? Right. Coming down from the right, how does it get to the other side? Right, we're in the bottom of a valley here. Right, so it's going to go over the lowest wall, the little wall. Right, at the lowest point. Right, because that, the red wall is going to be higher, right? So I can get through the yellow, where the yellow wall is, and then it's going to go to the bottom, isn't it? Right, goes to the bottom, hits the hill. What's it going to do now? Well, it's going to go round, but it's also going to fill up the bottom, isn't it? Right, it's going to build up, and it's going to build up high. Right, and then it's going to try and find a gap in the red wall to get out. Right, so it finds it there. Right, now where's it going to go? Right, it's got out of the wall. It's going to go back to where the river was, isn't it? So it's going to go there. Right, so a nice big blue blob, that could be a lake, it could be a wetland. Right, but it's the water level is built up. Right, those river patterns look exactly like what I would expect if this is a crater. Then we go up to the top of what I call the rebound hill. All right, where that rebound hill is should have been river alluvium. That is not river alluvium. And nor is the next hilltop next to it. I'm going to collect one of those rocks and have it tested soon, once I get my permit. Down the bottom of that hill, where the river bounces off, there's this cliff. I'm standing there looking at this cliff, and obviously on that occasion, I'm not going to walk down right to the cliff. I'm swimming through the pond to get to it. But my next visit, it was dry. I get down there. On the left-hand end, the fracture patterns are doing this. On the right-hand end, they're doing that. And in the middle, they're doing this. And the grain size, it's not quite volcanic glass, but it's getting there. I'm looking at this and I'm going, this is an explosion frozen in the rock. Frozen in the rock. And then, just to really throw a curveball into it all, this is on the southwest flank of the rebound hill. And I looked at these and I went, that's not breccia. That's conglomerate. What the heck is conglomerate doing near the top of a clearly melted hill? And what I think this is that the melted rock is lower and that there's still a layer of damaged but not melted rock above it that has been pulled up. Right? And on this hill, this is the only bit that's left, but that is probably the original riverbed. Now, again, I'm going to get that tested, see what they can make of it. But that is my current explanation for why those 6 rocks are sitting there on that southwest flank of the hill. But they don't belong on a landscape that is clearly a melted landscape. All right, remember sandstone, basalt, granite? The terrain shapes here are classic granite terrain shapes. All right, you look at the geology map and it says, this is all sandstone. I had another one of these hills in another crater, which I'm not going to cover, similar pattern, all covered in, the hills all covered in sandstone, but there is evidence of melting in the landscape pattern around the bottom. I felt like sending off an email to NASA and saying, you know that stuff you're talking about at Gale Crater, you're talking about it filling back in? Wrong. It's the original strata from underneath pulled up with the hill. That's my interpretation of what I've seen out there. I'm not a geologist, I'm a town planner, surveyor, and orienteer.